In this video I'm going to show you how to derive the Cauchy-Riemann equations from the first principles of differentiation. This should help your understanding of the Cauchy-Riemann equations by knowing exactly where they come from and why they work. So the basic idea, we're starting with a complex function. This is a complex function, just some function plus I times some other function, just call them u and v. Find its derivative. That's from differentiation from first principles. That's your standard expression. And the Cauchy-Riemann equations deal with analytic functions. That simply means that the derivative is not dependent on the direction that you take it. So if you're approaching in the x direction or if you're approaching in the y direction, it doesn't make a difference to the value of the derivative. And the way we're going to do the derivation is by taking this expression and finding it as you're approaching from the x direction as you approach from the y direction, and we know that they give the same value if they're analytic, and the Cauchy-Riemann equations are all to do with analytic functions. So we'll start with a substitution. So we're going to fill this equation in. So we've got z0 is just the point x0, y0. This is our analytic function. And delta z is your delta x plus I delta y. So a small change in x plus a small change in y, resulting in your delta z. Substituting in your z0, that's z0 here, we get this expression, and then z0 plus delta z, which is this bit up here, gives you this expression, just adding delta x, delta y from this. I will substitute all this into this expression. See, this is moved here and this has been substituted in there, and we can take out the i's. So put this and this bit together, so we get this expression. And we're going to find the limits in two different ways. So we're going to take the limits approaching from the x direction. This is the expression we've got in the last slide. And we're going to set y equals 0, delta y equals 0, and let x tend towards 0. So that's the way we're approaching it, along like that, which gives you this expression here. See, the delta y's become 0. I've got the limit as x goes to 0. And we can split this up across this plus sign, like so. And this will give you this expression here. Think about the basic idea of a derivative, which is this expression. In the top line here with the u's, you've got the value of a function u, where you've added some small value of x, then you're subtracting it without that small value added. So that's a very small change, and this is an infinitesimal change. So you've got kind of that ratio, which works out as this. Exactly the same thing here. Small change in v, and then subtracting the point before. So it's giving you a change. Which is that. Approaching in the y direction, very much the same idea. Setting x equal to 0 and letting y tend to 0, finding that limit as y goes to 0. So you're approaching the derivative in that direction. Those two different directions will give the same answer in a sense. They'll be equal to each other for an analytic function. So taking away your delta x's, you're left with this expression here. We can split that up just as before. Using the same rule, get this expression. See delta u and delta v. I've got the i's here cancelling. I've got 1 over I here. That doesn't quite look like a Cauchy-Riemann equation. There should be a minus somewhere. So we can multiply this through by minus I squared, which gives you this expression, which looks more like the Cauchy-Riemann equations. And we just equate the real and imaginary. We've found this by approaching in the x direction, and then this by approaching in the y direction. These have to be equal to each other because the function's analytic. We're assuming it's analytic because that's how you get the Cauchy-Riemann equations. They must be analytic. They must be equal for an analytic function. And so we're equating, this is the real parts here and here. Then the imaginary parts, got the coefficient I, which is that bit and that bit, which gives you these expressions, and they are the Cauchy Riemann equations.